Hi, I'm Evan Hartnett, and this is my Physics 2212 Lab 2 Lines of Charge lab report. The purpose of this lab was twofold. First, to use charged pieces of clear tape to observe the transfer of electrons between surfaces, and second, to produce a more sophisticated computational model of two charged tapes exerting an electric force on each other, and to use this model to estimate the amount of charge on each tape necessary to float one above the other. My results were that I determined the charge of each piece of tape to be Q is equal to 3.695 times 10 to the negative 8th coulombs. The physics principles applicable to this lab were Coulomb's law and Newton's second law to calculate the charge on each piece of tape, as well as the superposition principle. For this experiment, the system consisted of the two U-tapes and the surroundings were everything else in my room. I assumed that air resistance is negligible, pieces of tape are neutral until ripped off the table and charged. In the case of the floating tape, gravity and electric force from the other tape act on it in the y direction, resulting in a net y component of 0, and the charge was evenly distributed along the tape. This lab shared the same experimental models as Lab 1, which I'll briefly summarize here. The initial conditions were to place two pieces of approximately equal in length neutral tape on top of a third piece of neutral tape on the desk. This piece was charged by ripping them swiftly off of the third base tape. Then, a piece of tape was connected over two books and repelled using a second piece of U-tape. From the prior experiment, I observed that the U-tape pieces repelled each other, that they were attracted to my hand and other objects on my desk, as well as a negatively charged pen, indicating that the U-tape pieces are positively charged and therefore lost electrons when charged. Shown here are my data and calculations for this experiment. I recorded the length and the width of the U-tape, as well as the separation distance that caused the U-tape to float. I then calculated the mass of one piece of U-tape using the length and width. I found the magnitude of gravitational force by multiplying the mass of the U-tape by gravity, and then the magnitude of the electric force on the floating tape, because this quantity is equal to the magnitude of the gravitational force. I then found the charge on the tape treated as a point charge from my previous experiment using the shown formula. For this experiment, I found the charge on the tape treated as a line of charge via the formula shown for the electric field of a rod. Shown here is the final product of my computational model. The green arrows represent the electric field arrows going from the lower piece of tape, shown in blue as point charges, to the upper piece, the floating piece of tape, shown as red point charges. The white arrow represents the magnitude of the electric force from the lower blue charges onto the upper red charges. The yellow arrow represents the magnitude of gravitational force acting on the top piece of tape. I'd like to highlight a couple components of the code that I used for this model. The first picture shows the function line charge, which creates a line of n uniform point charges with a given total charge and mass arranged at equal intervals on a line segment starting at the start position and extending along the given axis. The picture below shows how I created the top tape, which was the red circles, and the bottom tape, which was the blue circles, with their associated inputs. The code shown here displays how I created the electric force arrow from the lower piece of tape acting on the upper piece of tape, as well as the gravitational force arrow acting on the upper floating piece of tape. Some discrepancies between my model and the experiment were that the charges on each piece of tape may have been unequal, resulting in differing values of Q, electric fields, and electric forces. Charge may have been lost to my hand or even to the air in my room. Weight was roughly estimated, and I used wider tape than was common for this experiment. Additional forces from surroundings were not accounted for. If I had modeled each of my tapes as a single point charge like in the previous lab, I would have gotten the following value for the charge on each tape: 1.98 times 10 to the negative 8 coulombs. This is significantly different from the value I got for the charge on each tape via treating the tape as a line of charge: 3.695 times 10 to the negative 8th coulombs. These estimates differ because they are different models. The line charge model applies the superposition principle by adding up small pieces of charge along the line of charge. The charge is separated evenly across the surface. Treating the tape as a line of charge is more accurate to how charge is distributed in reality and thus is closer to the real value than treating each tape as a point charge. To conclude, modeling objects as lines of charge is more accurate than modeling them as point charges, and they will have different values of charge. Newton's laws are still very much relevant when considering the impact of electric fields and forces. Objects can be charged from something as simple as touching another object. Electric fields and forces play major roles in the interactions between objects in our world.